Good evening all of you. So today our topic is harnessing the power of time series data. So before going further into the presentation, I would like to know how many of you have heard about Pulse, or how many of you have a sufficient understanding about how Pulse works and what are the capabilities of Pulse. Alright, so there are a considerable amount of people who have a sufficient understanding about Pulse, and of course at least you might have heard about Pulse, and of course there are people like who haven't heard about Pulse. But anyway, Pulse can be regarded as the main monitoring platform of Cake. It facilitates our production support engineers, our application support engineers, and our layer 1 and layer 2 teams by providing the proactive monitoring capability. Now, as you can see in this diagram, let's say one of our customer is suffering from some slowness in his device. So in that case, Pulse can detect that problem, and it can notify that problem to our application support engineer. Now in this particular scenario, we can see that like our application support engineer identifies this particular POS is experiencing high HDD usage. Now he decides now it's time to remove some unwanted log files to take back this particular device to normal state. So ultimately we are going to end up with a happy customer. Today I am not going to give you an introduction to Pulse or what are the capabilities of Pulse. I am going to give you an overview about a paradigm shift that we are going to do. This paradigm shift is going to be how we are going to move from proactive support or proactive monitoring into predictive support or predictive monitoring. Now the diagram at the top, it shows the same thing I described you before. So this is proactive monitoring. Customer is suffering from some problem, and Pulse notifies that problem to our application support engineer, and then it resolves that problem, and customer is going to end up with satisfaction. In the second diagram, or the diagram at the top, it shows predictive way. So here customer is unaware of like anything, so customer doesn't know what's going on, but at the meantime our application support engineer predicts about what's going to be the state of that particular device in next couple of hours or next couple of days or months. Then now in this particular scenario, application support engineer predicts, okay, this particular device is going to experience high HDD usage in next couple of weeks, and he thinks, okay, now I need to take some corrective actions, and he is going to provide the resolution. So now throughout this process, the customer's happy mood remains. So that's the beauty of predictive support. Now before moving into further details, I would like to give you an overview about the very high level architecture of Pulse. So we have deployed agent software in all 8000 plus device base, and each Pulse agent runs as a daemon, and it gathers various matrices from POS devices periodically. It captures various statistics. It captures system stats like CPU usage, memory consumption, then load average, and again open file count, such kind of data which is highly subjected to changes. At the same time, it gathers diagnostic data like whether any JVM crash has happened, whether any Moxie corruption has happened, or what's the status or what's the health of the sectors of hard disk, or whether that hard disk has experienced any bad sectors. So after gathering these data, agents send that data periodically to a central server, which is our Pulse server. Then Pulse analyzes that data and it checks whether that data exceeds certain thresholds or it adheres to any previously identified anomalous patterns. So if it is so, it's going to create Salesforce tickets to notify the application support engineer, and he's going to provide resolutions either by remotely logging into post device, or if that particular scenario needs any manual intervention, he can call our customer and provide the resolution over the phone. Before customer calls us, calls our customer like our customer support center and complains us. So the entire process, it's going to end up with the happy customers in. Now the problem is, now we are in a process of moving from proactive support to predictive support. Now the problem is whether our current data layer supports this. There are various problems that we have to address when moving from proactive support to predictive support. There are various changes that we have to do to our data layer. Let's see what are they. The first thing is, we need our data to be captured in a higher frequency. So why is that? Now let's say we have identified 2 incidents. Now let's say 2 unscheduled restarts have happened. Now in this case, do we have enough data points to see whether what has really what's the actual issue there? No, we don't. Currently we don't have. So if we capture data in higher frequency, we have enough data points in between those incidents to see to do a proper analysis on that event. So we can do a proper drill down if we have enough data points. And the other thing is, now in order to capture data in a higher frequency, like our servers need to withstand in higher request volumes. So currently during peak times, we are experiencing higher request volumes. So it's going to overwhelm our servers. So we have to overcome this problem as well. And then almost all data which is sent from Pulse is time bound. So this time boundness of data is very important, because in order to find precedence of data, we need data to be captured in form of time series state, and we have to store that in form of time series data in our data layer. And so this is another problem. Now whenever we are experiencing different problems, we are coming up with different hypotheses. Now let's say, now these days we are experiencing higher number of unscheduled restarts per week. So in that case, one set of people may say, okay, hard disk bad sectors cause unscheduled restarts. At the same time, another set of people may say, no, unscheduled restarts do not correlate to hard disk bad sectors. Now we are in a confusion. How to provide a resolution? Now, do we have enough data to see what has happened? Do we have enough data to see these correlations? Yes, we do. But the problem is, unfortunately, this data is scattered among multiple tables and multiple places. Now, in order to do a proper analysis by looking at the correlations, we need to combine those data. So that capability is not there with our current data layer. Finally, to do a predictive analysis, we need to look at data from different perspectives. In that case, we need customizable dashboards or sophisticated visualization platforms. Now let's see how we are going to address this. So any solution that we are going to come up with should address these things. Our solution should support inserting data in higher frequencies. That's the topmost requirement. And the other thing is, it should be capable of auto scaling to support traffic in peak times, because we are experiencing like high request volumes during peak hours or peak times. And the other thing is it should support powerful search joins and rich analytics in order to find like correlations between data. And another thing is we need to make this data available for search and analytics immediately, right? So whatever the solution that we are going to come up with should address these things. Now, after doing a lengthy analysis, we found out that time series databases or time series data layers are going to address this problem up to a considerable extent. Now, like we have done a lengthy comparison between these time series database types: Druid DB, InfluxDB, Elasticsearch. Of course, Elasticsearch is not merely a time series DB, but it has other capabilities as well. But it can provide time series capability very well. So here we have regarded it as again a time series DB. Now, when it comes to Druid, its cost is comparatively high, and the deployment architecture is also very complex. And on the other hand, InfluxDB, it's very expensive. So Elasticsearch, its cost is comparatively lower, and its deployment architecture is also straightforward. And Elasticsearch has another capability, that means it has a very sophisticated search engine called Lucene. So it can do like full text search very well. So anyway, our winner is Elasticsearch. Now we need to see how Elasticsearch addresses the problems that I have previously mentioned. Now let's see how Elasticsearch addresses the problem of like feeding data to our database in higher frequencies. Now in Elasticsearch, it has this hot worm architecture, and it can use high performance servers as data ingesting nodes at the high end. On the other hand, now we are experiencing high request volumes at peak times. So how Elasticsearch is going to address this problem? Now Elasticsearch can horizontally scale its cluster using shards. So this using this shard complex, the Elasticsearch can withstand in petabytes of data. Then the other thing is handling and storing time series data. Now when we are ingesting our data into Elasticsearch, so Elasticsearch underneath it uses this indexing concept, and when we are ingesting data to Elasticsearch, we are always creating like timestamps. We are always inserting timestamp as a separate field there. So in that case, this Lucene engine, it's going to create indices based on this timestamps. So whenever someone needs to see data in form of time series, Lucene can cater that problem, because we have already created indices by using timestamps. So that time series capability can be easily given with Elasticsearch. The other thing is how we can find correlations between data. So in order to do that, Elasticsearch provides this machine learning capability. Now Elasticsearch has a very sophisticated kind of visualization platform called Kibana, and like there's a separate plugin for that called Expect, and using Expect we can get this machine learning capability. Through that we can do supervised learnings and unsupervised learnings, and we can find correlations like between data. So during Vidulant's demonstration, he is going to like show you not about like using machine learning, but how we can find correlations. Now this is how Pulse came up with our own Elasticsearch platform, right? So like in our API we have a separate component to ingest data to our Elasticsearch cluster. So we have deployed in Elasticsearch in 2 zones to enhance the availability, and within a single zone you can see there's a high performance data node. So these are the high performance like servers which I told you before, which are like which we are using to ingest data into Elasticsearch, and we are also using high storage data node to keep like historical data, right? And Kibana to do like various analysis on that data. So then I'm going to hand over the presentation to Vidulan. He's going to go with a demonstration about what we have done so far with regards to Elasticsearch.
Hello everyone. So I'll start with what is Kibana. So Kibana is a visualization tool of Elasticsearch. So with that I can show you like currently over the past 4 months we have accumulated around 752 GBs of data, which are like 582 millions of data records. So with these data records you can see what we can see from this visualization tool. So my demonstration here will like a combination of both how we can get the general insights from this tool and how we can get the or prove the hypothesis that we are thinking of. So first I'll show you some general insights. The first one is payment cube re-architecture. So earlier the payment cube 1.0 was there in the production, so there were like too many issues with too many disconnections. The merchants have complained that they can't make the payment because of the disconnection of the payment cube. So then SWAT team has done the re-architecture of payment cube, that is payment cube 1.1. Now that they have sent that to the production in order to resolve the issue. So let's see how that is resolved. Is it resolved or not? So then if you want to see, so currently there are around 4,000 payment cube 1.0 devices, and also there are around 560 payment cube 1.1 devices. On that, the average disconnection count of payment cube 1.0 is 0.97, whereas for 1.1 is 0.14. So we can see it significantly the disconnection count is reduced, and also we can see day by day this purple chunk is the disconnection count, maximum disconnection count, and the top one is the maximum disconnection count of payment cube 1.1. So if you can see, every day the maximum disconnection count of 1.0 is a significant amount, like around 200, 176, it's almost above 100. Whereas for the 1.1 payment cube, the disconnection count is 11, 31 and 15. So which means the disconnection count is reduced, but the issue is not fully resolved, but to some extent the issue is being resolved. So what we expected is it will not disconnect forever, but we can see that to some extent it's disconnecting, but maybe that's due to the firmware updates or something.
But is that an average or is that actual numbers?
So this one is the actual number.
Okay, but that will depend on the deployment, right?
Yes.
Number of devices.
Yes, so this one is average. So average of 1.1 devices, and this is a maximum disconnection count of 1.1 device.
So that average there is 1.1.
Yeah, this is average.
That average is
That's average of 1.0.
similar average.
That's because there are like a lot of devices. There are 4,000 devices, and it has only 500 devices. So when you get the average, the number becomes very small.
Lower,
Yeah.
but you can't use the absolute number at the bottom because
So this is to see you to see the maximum disconnection. So if we want to see like if there any problem, we can see that from one device. So let's say, so if one device is disconnecting too many times, so that's a sample device. So if that is disconnecting too many times, we can say other devices can also disconnect for too many times. So there's a one device that has disconnected 31 times. So if you want to see,
That is for one device?
so this is a one device has disconnected 31 times. So if you want to see like past 14 days or past 30 days results, in last 30 days there is a device which has disconnected maximum 132 times, 130 times, one device.
Whereas there is another device on the older version that has disconnected
492 times. So that's a maximum disconnection count. This is not average, this is a maximum disconnection count.
For a device?
For a device, yeah. So then I'll go through the utilizations. So these utilizations is the first one is RAM usage and hard disk usage. So you can see there's a hike and drop every day. So this is a graph of last 14 days. In last 14 days you can see there's a hike and drop of RAM and hard disk. So why is that? So every day this time is a scheduled restart time. So in every scheduled restart, the device, the RAM is cleared. So which means there's a memory leak, and in every restart, the memory is cleared. So that's what it's happening here. And here, what's happening with the hard disk? So in every day before the restart, there's a CouchDB compaction purging. So you can see there's a hard disk is hiking, and then after the purging, it drops. But eventually, the hard disk is increasing. And this is CPU. So with the CPU, so there's a hike. So this hike is because of the operator was active during daytime, and there's a small hike here. And this hike is because of CouchDB compaction that's happening after operator is closed. And also, if you see, there are like three hikes, top three hikes. Those top three hikes are coming on weekends. So this is Friday, Saturday and Sunday. That's how the hikes are. So that's basically shows the operators how active he is. On weekends they are working too much. So that's a simple insight. And then also we can see alert distribution based on all the metadata. Simply just how many alerts we are getting based on different kernel versions and BIOS version. Likewise, we can get the alert distribution counts with the all different kind of versions we want to see. It's simply that. And another interesting insight is bad sector insights. So in last 7 days, we have like how many bad sectors issues have occurred based on hard disk models. So simply, so that's WDC, Western Digital. So Western Digital device, hard disk, there are like lot of bad sector issues. Whereas for Toshiba and Transcend SSD, there's a very low bad sector issues. And if we see, there are like around 1,150 devices which are affected by bad sectors in production, and in which there are like 1,105 pointers devices which are very old devices, and some data van devices. So it came with the time. The issue came with the time. So if we see so this one interesting pie chart. So here the inner circle is the hard disk models, and the middle circle is a device type, and the outer circle is the issues. So if we see, so this one, the one I highlighted is a bad sector issue. So bad sector issue has only occurred in these type of hard disk types. So if you see this, so this particular WDC hard disk model has faced, there are around 317 devices, and all 317 devices has faced bad sector issues. And also similarly for this WDC device, there are 531 devices. All these 531 devices are faced with hard disk issues. And interestingly, there's a Toshiba device which is also pointers. There are around 253 devices, and only 150 devices are affected with the bad sector. So if you are going to buy an external hard disk, go for a Toshiba one, I would say, unless you are going for SSD. So that's it with how we can get some general insights with this Elasticsearch and Kibana. Then I'll show how we can drill down into the issues. So for that we have created a dashboard called alerts. So in this alerts dashboard, first one is a cloud with what are the top issues that merchant is facing, and this is a heat map, and this is a time series. With the time we can see what are the alerts he has faced. So these are some charts I'll explain. So first we can see, so this is our search engine. So here we can search what we want and get the insights. So first I'm going to see how Moxie not found is correlated with other alerts. So if you enable this, it will create auto suggest also, so anyone can use it if you have no idea about it. Moxie not found. So it shows all the Moxie not found issues. So I'm going to see top devices which are affected by Moxie not found issues. So these are in past 60 days, these devices, this is basically MAC address, these devices are affected by Moxie not found issues. So click on this device, go to alert dashboard. I'm going to see for this particular MAC address, and I should change the time to past 60 days. So basically these are the top high level issues that the device is affected with, and this is Moxie not found timelines. So in these times he has faced with Moxie not found, and this one is a orange screen, so you cannot see this here. See, so this one is a orange screen issue. I'm sorry. So whenever there's a Moxie not found problem, Moxie is missing, so this obviously is going into the orange screen problem. So likewise you can prove this, simply you can prove this, and then I'll show you some unscheduled restart problems. So this is in this chart, each block is a device. So the block size is number of restarts the device has faced. Okay, so this is with the each every day, I mean for the last 7 days basically, and here we have the same alerts times thing. So if you want to see, simply select, I'm randomly selecting a merchant and applying. So when I select that, that will drill down into that specific device and the time. So this red color one is the restart spike. So here we can see there are too many restarts, so I'm going to further enhance into it. So I'm going to see what's this orange color hike. So the orange color hike is a JVM crash, and then the red one is a restart. So there's a JVM crash and there are 2 restarts. So which means it's this is our time. So 21:40 means our 9 p.m. That's the operator's working time. So operator has faced with some JVM crashes. Maybe his POS is not working, so he may have manually restarted the POS. So and then again also there's a JVM crash, and then he may have restarted the POS. So likewise we can see what's the reason for those unscheduled restarts. Likewise we can drill down into each and every device and see we may get the root cause. And then lastly I'll see whether we can see the reason for the Moxie unexpected kill. There be any reason or any correlation with that? Moxie terminated unexpectedly, and similarly I'm going to get the top devices. So I'm going to select one of these and add this into so the Moxie unexpected kill is there, and this merchant has faced with the CouchDB compression also. So I'll tell you the plan. So when we looked into this Moxie unexpected kill, so we saw some repeatedly each and every device is facing with CouchDB compression also. So in order to do that, so first device, so this device also affected with Moxie termination, unexpected termination, and CouchDB compression. So then I'm going to see some other devices also whether it's true. So this one also has this CouchDB compaction. So just to make sure, let's go for another one. This one also has the CouchDB compaction. So when I talked with like Moxie team, Tulya team basically, so they told there can't be any recent correlation between CouchDB compaction and Moxie termination, unexpected termination. But what we think is there's some other third party which is causing CouchDB compaction, or maybe after CouchDB compaction, like after 2 days, the Moxie termination happens. After not specifically 2 days, 2-3 days, it happens. So there can be some correlation. So some third party who is causing CouchDB compaction, and then the method we are going to resolve the CouchDB compaction, which may cause the unexpected kill. So for that, further we are going to collect some data about Moxie, like WOM scores and file count, open file counts for Moxie and libset user. With that, we can verify who is the real culprit here. So yeah, that's with my demo. So anyone can use this. This tool is open for anyone. So if anyone is interested, yeah, you can play with this. And yeah, so there's something with the slide also. Yes. To finish off with the slides, so all thing that I have showed you is a manual work. So we are like manually seeing the correlations and going to make sure we are going with the correlations. But this can be done automatically with the power of machine learning. So Kibana is giving to us, but that is unfortunately not available in the open source version that we are using. So when we are getting the Elastic Cloud, the Platinum one, we can get the access to the machine learning also. So it will find all the, it will automatically model the everything and detect anomalies, and it will find all the correlations. So likewise with the machine learning of Kibana, we can do everything automatically. Apart from that, we can download the data that we have stored, all those 800 million, 500 million data we have stored, and we can model our own thing, own models, and we can find the correlations as well. So that's